Let's talk about another example of an electrophilic addition. This one's called a Markovnikov hydration, and we would use catalytic acid and water to accomplish it. So Markovnikov hydration, the Markovnikov part of this means that the reaction follows Markovnikov's rule. We'll just say follows M's rule, meaning that the hydrogen attaches to the less substituted alkene carbon. This is a hydration because we're adding the elements of water across the alkene. So looking in the box, we start with an alkene. We're going to treat it with water. Okay, so we can see that the elements of water, H2O, add across the alkene. And this is going to be in the presence of a catalytic amount of a Bronsted acid. So let's put that in, that this is a Bronsted acid. And so you can see this written in different ways. So people might just write cat. That means catalytic. So you'll have a very small amount of the Bronsted acid relative to everything else that you have in there. Or you might see TR. That means trace. So again, a small amount. Or it could be reported as some small percentage, like 1% or 2% or something like that, also indicating a very small amount relative to everything else you have in there. Now, the acids that you would use would be the following. First of all, you're going to need to use a strong acid because the alkene is only weakly basic. So you need a very strong acid to be able to protonate it. So that's going to be things like sulfuric acid, nitric acid, and then this guy, TSOH, which is called tosic acid. Tosic acid is an acid you haven't seen before, but it has a similar structure to that of sulfuric acid, and it's a strong acid. So the structure of tosic acid looks like this. So that's tosic acid. Tosic acid is a solid, and so it's very easy to use, and a lot of organic chemists will use it as a Bronsted acid catalyst. All right, so let's see what happens in the reaction. We're going to look through a mechanism. So first of all, notice that the OH group attached to the more substituted alkene carbon. So that's another way of expressing Markovnikov's rule. Now, when you have a Bronsted acid, a strong Bronsted acid in water, let's say sulfuric acid, remember that what you have going on is the following. The sulfuric acid will donate a proton to water. That gives you H3O+, and then of course you have the conjugate base of sulfuric acid, which is bisulfate. It's H3O+, that's the proton source in the reaction. So in the first step of the mechanism, what's going to happen, actually, let's back up just a second. The mechanism is going to largely follow exactly the same pattern you saw with the addition of HBr or HCl across a double bond. There's only going to be one difference, which is a proton transfer, but that's easily accommodated, and so we'll see that once we get to that step in the mechanism. So you'll recall that in the first step of the mechanism of the addition of HBr, what happened was that we protonated the alkene, and that's what happens here as well. So we have H3O+ as the proton source. So let me draw out H3O+. But then we can also draw it like this. So proton attached to OH2 with a positive charge and one lone pair, so that we can employ it in the mechanism. So the alkene uses the pair of pi electrons to accept the proton from H3O+. Because it's a Markovnikov addition, the proton attaches to the alkene carbon that has more protons. So it attaches to the less substituted alkene carbon, which means that the carbocation forms on the more substituted alkene carbon. So we have a tertiary cation that we formed this way. So what happens next is that the water that you have in the reaction mixture can now act as a nucleophile, and it's going to attack the carbocation. So we start an arrow at the lone pair, one of the lone pairs on the oxygen and water, and point to the carbon with a positive charge. That's showing that a bond is forming between oxygen and carbon. Now, everything else that was attached to that oxygen comes along for the ride. So that's the two protons, the other lone pair, and of course that means that once the oxygen bonds to the carbon, it develops a positive charge. To complete the reaction, another water molecule comes along and pulls a proton off of this intermediate. So you end up with the alcohol. And the regenerated acid catalyst. And then we can redraw the alcohol, omitting the hydrogens and just using the skeletal format. So that's the same product that we just got. Okay, let's look at the role of water at different points in the reaction. In the upper right, the step where the water attacks the carbocation, it acts as a nucleophile. Meaning that it bonds to carbon. However, in the subsequent step, it accepts a proton. Another water molecule accepts a proton from that intermediate. So here, water acts as a Bronsted base. Meaning it bonds to hydrogen. Okay, let's look at some examples of this reaction, draw some mechanisms, predict some products. So this is an acid-catalyzed hydration. So let's look at a set of conditions. So one of the most important things that you're going to be learning is how to recognize the conditions that you have so that you can fit them into a reaction category. So let's say that we start with this alkene and we combine it with sulfuric acid and water, and let's say we have a small amount of sulfuric acid. Now, if they don't tell you 1% or 2% or catalytic or trace, if they just say sulfuric acid and water, that's okay too. In fact, most things are going to say that, but you might see it more explicitly described. Okay, so a few things here. First of all, you recognize that you have an alkene, and because you know what the characteristic reactions of alkenes are, you know that this must have something to do with an addition reaction. So it's going to be an addition reaction. The second thing is that you look at what's around the arrow. So you have a strong acid and water. So to a chemist, what you really have is H3O plus. Anytime you have H3O plus, you always have water. So in some reactions, okay, maybe instead of writing H2SO4 and water, somebody could have just written H3O plus. That would imply that water was also present. What we know about H3O plus is that this is a strong acid. So we'll say SA for strong acid. In the presence of a strong acid, so if you see a strong acid in your reaction mixture, the first thing you want to do is look for a weak base to get protonated. So in the presence of a strong acid, look for a weak base, WB, to get protonated. So the only thing that we have in there that's weakly basic is the alkene. So of course it's going to be the alkene that gets protonated. You're going to follow exactly the same pattern that you saw on the previous page. All the mechanistic steps are exactly the same. So in the first step, the alkene accepts a proton from H3O plus. The proton is going to attach to the less substituted alkene carbon, and the more substituted alkene carbon is going to form a carbocation. In the second step, a water molecule acts as a nucleophile and attacks that carbocation. In doing so, the oxygen atom forms a bond to the carbon that had the positive charge. The hydrogens and the other lone pair that were attached to that oxygen come along for the ride, and you get this intermediate. That intermediate is then deprotonated. And that gives you the product, which is an alcohol. Notice that I'm drawing the product as a skeletal format, leaving out hydrogens. Remember, we don't have to draw those explicitly. Okay, now as another aside, let's talk about this intermediate briefly. This is nothing more and nothing less than ROH2 plus, which from the acid-base section, we recognize as being a strong acid. So this is a protonated alcohol, which is a strong acid. Let's do another example of this. Okay, so you're confronted with this set of conditions, an alkene. So because it's an alkene, you know it's going to undergo an addition reaction. And that's in the presence of nitric acid, which you know is a strong acid, and water. So the first thing is that a strong acid in water is H3O plus. So that's how you would interpret that. Let's draw in the hydrogen on the alkene so we can keep track of more and less substituted carbons. And so this is going to follow the same pattern that we've seen in the previous two examples. Step one, the alkene is protonated. The carbocation forms. on the more substituted alkene carbon. Following that is an attack by the nucleophile water. So water performs a nucleophilic attack on the carbocation, forming a bond to it. Everything attached to the oxygen comes along for the ride. And then another molecule of water acting as a Bronsted base removes a proton from this intermediate. That gets us this product. So notice how in all three examples, the mechanism was identical. Notice also the similarity between this mechanism and the mechanism for the addition of HX across a double bond. That's because they're both electrophilic additions. So these are both electrophilic additions, and so they're going to follow the same mechanistic pattern. Okay, now that we know a few things about carbocations, we can start getting into some trouble with them. Carbocations, as it turns out, as we know already, they're reactive intermediates, so they're fairly unstable, but they can also be kind of messy. And what I mean by that is that they can undergo what are called rearrangements. So these structural rearrangements, in the case of a carbocation, can be described as what's known as a 1-2 shift. What that means is that an atom or a group of atoms moves from one carbon to a neighboring carbon. Okay, let's look at the overview of carbocation rearrangements so that we know how to draw the mechanism and where to look for these, and then we'll start looking at some examples. So remember that the carbon that has the positive charge is the alpha carbon. One bond away, those are called beta carbons. So what happens, let's put a Z at the end of this bond right here, is that a group, and that could be an alkyl group, or it could just be a hydrogen atom, migrates from a beta position with the bonding electrons. So what this means is that this, with these electrons, are going to move over from the beta carbon toward the alpha carbon. So at the end of the day, we're going to end up with this. So essentially what's happened is that the positive charge and Z with its pair of bonding electrons have switched places. So when Z and its pair of bonding electrons moves over, it leaves the positive charge behind while satisfying the positive charge that was on the alpha carbon. Let's look at some actual examples of this, starting with this one. Okay, so this carbocation has a positive charge on this carbon right here, which is the alpha carbon, and one bond away are beta carbons. Now this is a secondary cation. That's going to be important to keep track of. So this is a secondary cation. So what's going to happen here is that a hydrogen with a pair of electrons that bonds it to that beta carbon is going to move over. So we start the arrow at the pair of electrons and we point to the alpha carbon. When it moves away from that beta carbon, that leaves that carbon with a positive charge. Now we have a tertiary cation. So when it's a hydrogen with a pair of bonding electrons that moves over, we call that a 1,2 hydride shift. 1,2 because it's moving from one carbon to a neighboring carbon. Let's look at what's called an alkyl shift. So as the name suggests, that's just going to be the migration of an alkyl group. Now I'll use methyl groups because they're smaller and easier to draw. But it could really be any alkyl group. So we're starting out once again with a very similar carbocation. This is a secondary cation. An alkyl group, in this case a methyl group with a pair of bonding electrons, can move over. So we start an arrow at the bond, point to the carbon with a positive charge. So what gets left behind is a positively charged carbon. And here's the new position of the group. Notice that what we got to here with the tertiary carbocation. Okay, now as you can imagine, this can get really messy really fast. So we're going to make some simplifying assumptions. Now in real life, there are exceptions to these things, but this is going to handle most of the cases that we're going to see, actually all of the cases that we're going to see. And so this is a good starting place for understanding things about carbocations. So what we're going to do is if we're drawing a carbocation rearrangement, we're always going to be rearranging from a less stable cation to a more stable one. So always rearrange from a less stable cation to a more stable cation. Now in real life, sometimes you can get a rearrangement from between two cations of equal stability. We're not going to worry about those cases. We're going to go from less stable to more stable in all cases. Another assumption we're going to make, or a rule that we're going to follow, is to only have one rearrangement. Now again, in real life, that's not always the case. So sometimes a carbocation can rearrange and then rearrange again. And sometimes even after that, it'll continue to rearrange. But for the cases that we're going to see, a good simplifying assumption is to do one rearrangement and then stop there. And then finally, another assumption that we'll make is that these carbocation rearrangements are going to be irreversible, which means there's no reverting to the original carbocation. Now again, in real life, you can find exceptions to these things, but these are going to cover the vast majority of cases that we're going to see. So we'll all follow these rules so that we're all on the same page. Okay, let's take a look at a reaction mechanism now where there's a carbocation rearrangement. So we're still thinking about electrophilic addition. We're going to go back to the original reaction that we saw, which was the addition of HX across the double bond. So we have HBr and we have an alkene. And so we know that under those conditions, the alkene is going to get protonated. That's going to be the very first thing that happens. So we draw that mechanism, starting an arrow at the pi electrons in the alkene, pointing to the proton, breaking the bond between H and Br towards the bromine. The cation is going to form on the more substituted carbon. That's the one that I've highlighted. So we draw that first. Now remember that this proton is also attaching. It's attaching to the less substituted carbon. But at this point, we've drawn the mechanism several times, And so we know that it's attaching. We don't necessarily need to draw it. All we really care about is where is that positive charge? We know that the hydrogen has gotten attached, otherwise there wouldn't even be a positive charge. So here's the positive charge. Now let's label alphas and betas. So the one with the positive charge is the alpha. One bond away are beta carbons. Okay, if we were to move something from the beta carbon on the right, that would be a hydrogen, so it would be a hydride shift. And the positive charge would end up on the carbon on the far right. Now what we're starting out with is a secondary carbocation. But if we pulled a hydrogen from the carbon on the right, the beta carbon on the right, we would end up with a primary cation. So we don't want to do that. So let's look at the beta carbon on the left. It has 3 bonds to alkyl groups, but it also has this bond to a proton. If we move that one over, then it leaves behind a tertiary cation. So let's draw this one in so that we remember where it came from and where it went. And of course that already had a hydrogen in that we had not drawn, that secondary cation. So now we have a tertiary cation. So we followed the rule that we're going from less stable cations to more stable cations. At this point, the bromide ion, which was released in the first step, can act as a nucleophile, just like we saw in the original example of this reaction mechanism, and attack the cation. So we end up with this. Okay, so what we should note here is that we see very little, if any, product that comes from the cation that we formed initially. It rearranges way too fast to allow the bromide ion to attack it. So no product from the initially formed carbocation, and that is simply because it rearranges too fast, faster than the bromide ion could attack it. Think about it this way. The hydride shift that's taking place within the molecule is taking place within the same molecule. So the hydrogen is right next door to the cation. By contrast, the bromide ion is separated from the carbocation. Now, it might not be that far away, but it's certainly farther than that hydrogen is. So the hydrogen's closer in, it's within the same molecule, so that's going to be a faster step. Okay, let's look at another example or two. Okay, here's an example. There's an alkene. But you also see some double bonds in the benzene. Okay, so we need to talk about benzene a little bit here before we can move forward. The double bonds in benzene don't react the same way as the alkenes that we're talking about. So benzene's double bonds have their own way of reacting that's not the same as any other double bond. So they don't react like regular alkenes. In this section, we're just talking about the reactions of regular alkenes, not the ones in benzene. So what this means is that that benzene ring is going to stay intact in the product. So we're just going to pull it through the whole mechanism and pretty much ignore it. It's like a rock that's attached to the molecule that it's not going to change. Now we look at the arrow, and what we see is that we have a catalytic amount of nitric acid in water. So automatically, we think H3O plus. So an alkene, in the presence of the strong acid H3O plus, we've already seen is going to get protonated. So we protonate it. And because the reaction follows Markovnikov's rule, that means that the cation ends up on the more substituted alkene carbon. Okay, so we have here a secondary carbocation. There's an alpha carbon, and here are the beta carbons. The beta carbon on the right has 3 hydrogens attached to it. If one of them moved over, it would leave a positive charge behind. So the beta carbon on the end would have a positive charge. That would be a primary cation. That's not more stable than what we have. In fact, it's less stable. So let's look at the beta carbon on the left. If a hydrogen from that carbon moved over, relabel stuff so I have room to write, what would we end up with? So remember, when something moves away from a carbon in a carbocation rearrangement, it leaves a positive charge behind. Or you can think that it just switches places, essentially and effectively, with the positive charge in the existing structure. Okay, so here we have this cation. Well, this one is also secondary. So have we gotten a more stable carbocation? In this case, the answer is actually yes, we have. The cation that we just formed, although it is also secondary, like the one that we started with, the positive charge is on a benzylic carbon. So this cation, unlike the one that we started with, is stabilized by resonance. So this is a secondary benzylic cation. It's more stable than what we started with because it's stabilized by resonance. Now, we had a strong acid and water in our reaction mixture, so this is going to be a hydration. So at this point, we can draw the rest of the mechanism. So water acts as a nucleophile and attacks the carbocation. And then the last step in the mechanism is the deprotonation. Okay, let's work on one more example, and that's this one here. So again, recognizing patterns, recognizing the key components of the chemicals that you have in a reaction mixture. You have an alkene and you have HCl. So first of all, HCl is a strong acid, so you know that something is going to get protonated, and the thing that's going to get protonated has to be a weak base. The only weak base you have would be the alkene. So the very first thing that's going to happen is the protonation. Okay, when this gets protonated, the proton attaches to the less substituted carbon, and the cation, the carbocation, forms at the more substituted. So that gives us this. This is a secondary carbocation. Now you might have noticed that so far, all the carbocations that we've ended up rearranging have started out as secondary cations. So it's a good point that if you form a secondary carbocation in a reaction, you should look at the beta positions to see if there's a way to rearrange it that's going to give you a more stable carbocation. So the carbon with the positive charge is alpha, and here are the beta carbons. From the beta carbon on the right, we could move a hydrogen, but that would leave us with a primary carbocation. So that's not an acceptable move. There's a hydrogen on the beta carbon on the left. So we could move that over. And that would give us a more stable tertiary carbocation. So that's certainly one thing that could happen. However, there's another possibility here. So I'm going to redraw the carbocation down here. So this is the one that was initially formed. And I'm going to put numbers like so. Okay, in the previous rearrangement, let's track what we did. We moved this hydrogen with its bonding electrons over, and so they end up over here. So anything that's attached to a beta carbon can move with a pair of bonding electrons. So although the rearrangement that we just drew is perfectly acceptable and is probably happening to some extent, there's another one that's even better. And that would be the one where you move one of these bonds. Now it doesn't matter which of those you move. Either one is going to give you the same product. So let's just move this one here. Okay, to draw the result of that, let's keep all the atoms in the same positions. And let's number things. So 1, 2, 3, 4, 5, and 6. So the electrons moved from between C3 and C4, and now they're between C2 and C4, which means that they moved away from 3, and so it has a positive charge. Okay, now that is not like a typical organic structure, so let's clean this up a little bit. We can see we have how many carbon atoms? 2, 3, 4, 5, 6. That's 5 carbon atoms. So this is a 5-membered ring with a methyl group sticking off of it. The methyl group is 1. Here's carbon 2. That's connected to 3. 2 is also connected to 4. And 5 is connected to 4. And 6 is connected to 5 and to 3. The positive charge, remember, ended up on 3. Now to go back up here, remember we started with HCl, and so at this point, a chloride ion can act as a nucleophile, attack the carbon with the positive charge, oops. And we have to take into account that we have a new ring size now. And we get this as the product. Okay, so a few things. We started with a secondary cation. When we rearranged, that's still a secondary cation. So again, did we get any stability? Is the new cation more stable? The answer is yes, because we went from a 4-membered ring to a much more stable 5-membered ring. Remember that going from a 4-membered ring to a 5-membered ring relieves considerable ring strain. And so this is going to be a very favorable process. Now you might look at this problem and think, well, how would I know to do this move? How would I know to do this carbocation rearrangement? First of all, this is a specific kind of rearrangement that sometimes people will refer to as a ring expansion. It's called a ring expansion because you're making the ring bigger. And you can also have ring contractions where you make the ring smaller. Those types of things are going to be favorable if you're moving from a 4 to a 5-membered ring, or from a 5 to a 6-membered ring, or if you're moving down, say from a 7 to a 6, or something like that. Actually, 7 to a 6 is all you would see. Okay, so to answer the question, well, how am I going to know if that's going to happen or not? At this stage of the game, you may not. And so a question like this might be framed in the following way. It might give you a starting material and a set of conditions, or reagents, and a product, and ask you to propose a mechanism. So it tells you what's going to happen, or it tells you what you want to rationalize. It doesn't ask you to predict a product, because in this case, there are different things that could have happened, and so there's different products that we could predict. There's not one clear major product. So cases like this, we'd probably ask you instead, here's a product, and we're not saying that it forms as the major product, or maybe not very much of it forms at all, but we're trying to understand, well, how did this form to begin with? And so we want to propose a mechanism for its formation. So a problem like this is more likely to be framed in that way.